Hi everybody. I'm Ningombam Chandrachani Devi, and I'm an assistant professor at Department of Physics, Manipur University, Manipur, Imphal, India. First of all, I would like to thank the organizer for giving me an opportunity to present my work. Today, I'm going to talk on the topic nonlinear structure formations of dynamical dark energy model. This work has been done in collaborations with some of my collaborators in Mexico. So why do we need to consider the dynamical dark energy model instead of Lambda CDM? To address these questions, I would like to highlight the result from the DAISY 2024 constraint on the equation state parameter, the parameter which used to define the dark energy model, and which W equal to -1 corresponds to the Lambda CDM model. So one can see easily from the figure. The figure corresponds to the parameterization done for the Turing dark energy model. In the recent result of the DAISY, which is the BAO, in combinations with the cosmic microwave background radiations and the supernova observations, suggest a preferable preferal on the dynamical dark energy, which is a deviation from the -1. And also we have a Hubble tensions with the Lambda CDM model. Why do we need to study the nonlinearism? What is the importance of the nonlinearism is that the study of the nonlinearism become important either through the two-point correlations or power spectrum, which provide direct connections between the theoretical model and the observations data. And in order to understand the effect of the dark energy on the structure formations, on the evolution of structure formations, it is important to study understand the dark energy dynamic. And dark energy dynamic can simply understand by looking at the evolution of the equation of state of dark energy. Equation of the state is nothing but is the ratio between the pressure over the density. Here I'm showing the evolution of equation state parameter for different parameterizations, such as the VA. VA is the Bose-Alkermes parameterizations, exponential type parameterizations, the log, and the JVV, which has a polynomial type parameterization, along with the Chevallier Polarski Linder parameterization, which is also called as the CPL parameterization. So one can see from the figure there is a transitions from the higher negative value of the equation of state towards the lower negative value of equation of state. So they're kind of having a transition from the phantom-like behavior towards the quintessent type dark energy model on such parameterizations. For our case, we are going to consider the dark energy model, which have a 4-parameter. And the importance of this 4-parameter parameterization is that by choosing the specific value on the Q and the jet T, we can have smooth transitions as well as sharp transitions. So the main idea is if dark energy has some kind of soft transitions, stiff transitions, then will it able to capture such behavior on the structure formations. So for our clarity, we also we also check the matter perturbation theory first, and the evolution of the matter density evolutions first and the second order. And here we define the two model, SEO SEoS-I and the SEoS-II, which is the stiff equation state model 1 and the model 2. So model 1 corresponds to the stiff equation state with the Planck best fit value of omega matter and the H0 value. And the model 2 corresponds to the to its own best fit value of omega matter and the H0, which are a little bit higher compared to the Planck best fit value. And the CPL corresponds to the best fit value from the Planck. And here we show the growth functions and the first and the second order. So one can see here the for the CPL and the model 1 have a lower growth compared to the Lambda CDM, and model 2 have a higher growth factor in both order at the lower redshift, implying the faster growing mode compared to the other model. So this effect will be seen in the structure formations. Here come the specifications of the simulations. And as I mentioned before, the stiff equation state model 2 corresponds to the one which has a little bit higher value of omega matter and H0 value. And for the simulations, we run the simulation box of 1024 H inverse megaparsec and length, and the simulations particle number we use 1024 cube and the mass of 1024 cube, and the initial ratio we set on the 49th, and we run with the time step of 200, and different snapshots are taken out at a different redshift. And for each model, we have 5 runs. So there is a 5 realization for each cases. So nonlinear evolution of large scale structure. In order to understand, for this we have to run the hydro simulations. For our case, instead of hydro, we are going to run the dark matter simulations. And if we want to compare directly with the galaxies, then we need to populate the dark property of the galaxy on this dark matter output later on. For our purpose, for the initial conditions, we use the 2LPT initial condition generator, and where we input the power spectrum of our model from the modified CAM. And for the full n-body simulations, we use the COLA code, co-moving Lagrangian accelerations, which implemented the Lagrangian perturbations theory on the simulation step. So after the simulations, we take out the snapshot at different redshift, and at that snapshot, we run the Hello Finder called the Rockster to get the Hello catalog. In the n-body simulations, part mostly is based on the particle maze. In the particle maze approach, the Poisson equation is calculated with the mass approach. First, the density density on the mass is calculated. Once the density is calculated, we can calculate solve the Poisson equations. And once we have the potential, then from differentiating the potential, we get the force. Once we have the force, we can interpolate back to we can force the particle to move, and the particle will get to new positions. And again, the whole process will repeat, finding the density for these new positions of the particle, then the Poisson, solving the Poisson equations, then again back, then the potential, then the force, then back again for the next step. However, in the case of the COLA approach, instead of calculating the poisons, rarely there is a calculations different. We can in COLA calculate the difference between the full simulations and LPT, which make faster, accurately recover and equality. The advantage of the COLA code is it accurately recover the large scale structure within few times shape, and so as the less use of the computational resources, and it is much faster than the usual simulations. One can see from the figure, the figure is taken out from the COLA paper, and here you can see in the middle figure that within the time 10 times that how the COLA approach try to map the large scale structure compared to the gadget time step high resolution simulations. Here comes the result. Here is the nonlinear power spectrum of the dark matter particle, and for three different redshift. And we can see for the case of the step equation state model 1, there is, and CPL, there is a depletion in the power with respect to Lambda CDM, and it is mainly due to their dynamic of dark energy, overall less negative value of the equation state, and highly larger Hubble expansion that trigger a slowing down in the growth of the structure. However, for the case of the model 2, the behavior is quite different. At the linear scale, it has a deficit in the power, but it turned out to be increased later on. And the difference between the deficit in the power from the Lambda CDM reduces with respect to the redshift for the CPL and the model 1. Here come the Hello mass function. Hello mass function, it's nothing but the calculation of the number of mass per unit, some particular mass being. Again, we can see for the CPL dynamical dark energy model and this step equation state 1 model, there is a less number of the bound halos. The lower growth of rate of the matter density of this model result into less number of the bound halos. However, the growth rate for the model 2 is higher compared to compared to Lambda CDM. So as we observe the higher number of the bound structures over here and throughout all the three redshift. And here come the 2-point correlation functions. So we see the difference of 1 to 2% difference for the Lambda CDM and this, with respect to Lambda CDM for the step equation state model 1 and the CPL, and it's observed up to 1% difference at R equal to 60 megaparsec H inverse. However, for the case of the model 2, there is a huge significant difference throughout all the R scale, and much different is about at the 60 R H inverse megaparsec scale is about 60% different is observed. And what I would like to mention here is that what the transition, shaft transition, which we appear for such model was not observed in the structures. So in summary, I would like to say that we explored alternative cosmological models, including the stiff equation state and the CPL dark energy model. On studying the nonlinear evolution of the universe, we found a duplicity in the power spectrum with respect to Lamda CDM throughout all the K mod for this equation state 1 and the CPL model. The difference remained within the 1 and 3% at redshift 0. So there is a possibility to distinguish them within the few percent of 2 to 3 in the power spectrum, as well as in the 2-point correlation and the Hello mass function. So no significant imprint of the stiff transition in the dark energy field is observed in the structure. However, the behavior of the last deviation of stiff equation of state model 2 is observed with respect to Lambda CDM, and it is mostly because of the variations in the omega matter and H naught value. The chances of distinguishing between this model increases at the high mass end. So having a tool to study the large-scale structure based on the n-body simulations and that run at the low computational cost and simultaneously recover the large-scale structure recurrently would be useful to provide the constraint on the dark energy model. And with the presence of large alternative model of dark energy, such simulations would be an efficient way to constrain the model. So this is the start. We are working on cooperating all the other parameterization form of dark energy model in the COLA code. Thank you.